Hey everyone, good morning. So while the slides come up, my name is Beau Compton. I'm at NASA Glenn Research Center, and I'll be introducing my project to the European Lunar Symposium. I've presented it at other ISRU conferences, but it is the Cutlass project, carbon utilization technologies for lunar and atmospheric systems. A little bit of a mouthful, but we kind of cover a lot of scope here. There we go. So this project covers something called the Bosch process, which we think could be applicable to a lot of different situations such as ISRU. And so that's going to be a lot of the focus of this presentation, but we also actually have some terrestrial applications as well. So just an overview of the Bosch process itself. I guess first of all, for ISRU, so oxygen and carbon powder are identified as important products that could come out of ISRU processes. So oxygen, of course, that could be used for propellant. It could also be used for breathable air. Carbon actually has some interesting uses as well. I'll kind of expand on that in the end, but uh, I guess just a brief overview that carbon could be used for electrochemical processes. It could be activated to become like a filter and absorb different gases, so things like that. The general Bosch process here. So that's the overall chemical process, but there is some nuance there. So don't hang on to that reaction too much. But typically, that's what the Bosch process looks like in a lot of applications. And once again, we also think since we have this CO2 here on the left side, if we can capture CO2 from the Earth's atmosphere, we could actually use this process as well, as long as we can electrolyze and recycle the hydrogen from the water. So a lot of people have looked at the Bosch process before, but no one has really delved too deep into the ISRU applications of this process. Typically, you see this applied to life support systems. Um, so we're, as far as I know, some of the first to look at actually designing, integrating, scaling, actually testing this technology within this context. Uh, so uh, in I guess the near term and longer term, so the Space Technology Mission Directorate at NASA, one of their upcoming missions is called Lift One. That's going to focus on actually producing really any quantity of oxygen on the lunar surface. And so there's a lot of candidate technologies that will be coming up, and hopefully we can be one of those technologies that supports some of the main oxygen production technologies. So in the lunar application in particular, and I'll kind of expand on this in another slide. And then that's why I said not to really hang on to that one chemical process, because we kind of have to modify it a little bit, because what we think this technology can do is actually be integrated with carbothermal reduction, because you don't just need methane to facilitate the carbothermal reduction process. You can actually use carbon powder instead. So that's kind of an alternative method for this technology, and we think we can provide that carbon feedstock, and then that carbon monoxide that comes off of the carbothermal reduction reactor can go back into our Bosch process, so it kind of closes the loop on the carbon. In the longer term, we also think this could work on Mars as well, due to the high CO2 levels in the Martian atmosphere, so approximately 95% CO2, so that gives us plenty of reactant to work with. And so we think we can use the full Bosch process to produce that oxygen and carbon powder straight from that process. So I don't think I need to tell everyone here, but CO2 levels are rising here on Earth. They are going about over 420 ppms at this point. And one of the contributors to that is post-combustion industrial flue gas. So we think that that's kind of the, I guess, lowest hanging fruit here for our technologies because that's some of the highest CO2 concentrations that are being produced. So overview of Cutlass itself. So we're developing different components of the Bosch process, as well as integrating some of those technologies. Once again, I'll kind of elaborate these further, but so one technology here is the chemical reactor that actually produces the carbon and water here. So that's the carbon formation reactor. So then we also need to acquire the CO2. And so our device here is, we call this it's absorption pump, the rapid cycle temperature swing absorption pump. We also have a solar thermal receiver subsystem. You can kind of see there. So in this particular application of the Bosch process, we are looking at using solar thermal energy via solar concentrators. It's not necessarily required for this process to work. You could use photovoltaics, things like that. But that's what the route we wanted to go down for this project. So we're integrating the carbon formation reactor with some more heat exchangers to improve the efficiency and yield of our products. We're also integrating that solar thermal receiver subsystem with the CFR to show that we actually can put those together and they do work. We're also integrating both of the chemical reactors that are involved in the full Bosch process, and I'll show the architecture so that hopefully makes a little more sense. We also have a pretty large modeling effort for the Cutlass project. So for ISRU environments, so that would be lunar and Martian, and terrestrial. So we're kind of creating system level models that are ideally anchored to the data that we get from our project. Okay, so here's the architectures. So I won't go through every single detail here. Sorry, this is not the most legible. Hopefully y'all can see this on screens. So I'll actually start on the right side. So that's kind of like the typically what you see of a full Bosch process. So this is kind of simplified. So there's definitely some more nuance there. But it starts with our CO2 absorption pump that absorbs CO2 from the Earth or Martian atmosphere, goes into the solar thermal receiving system. So that's going to heat it up to the reactant temperatures that goes into the reverse water gas shift. So that would be, I believe, approximately 700 degrees Celsius for the reverse water gas shift reactor. That also produces water, so that's condensed. And that water is electrolyzed. So we also have a gas separation device, which is not really in the scope of Cutlass. We don't exactly have anything designed quite yet for this system. But then after that gas is separated, then that goes into the second reactor that we're developing, the carbon formation reactor. And so that operates at approximately 475 Celsius. And that's where the actual carbon powder is produced. On the lunar side, so you can see that this is modified from the full Bosch process. So right here is the carbothermal reduction reactor. And so if you use carbon powder as the carbon source, that will produce carbon monoxide and CO2. And then that goes directly into the carbon formation reactor, and we basically take out the reverse water gas shift reactor at that point. Essentially, after that water is produced, it's condensed, and then the gases are fed back into the carbothermal reduction system. Okay, so the absorption pump itself. Essentially what this is a stacked plate heat exchanger. You see in a lot of different industries, but what we're doing here is we get a very thin coating of zeolite, which is a CO2 adsorbent. And the idea is that we can really rapidly cycle those layers, and hopefully by doing that, we can bring down the system mass and bring up the efficiency, because zeolite is a very poor thermal conductor, but you need to actually swing the temperature of that to adsorb and release CO2. So this is the rapid cycle temperature swing adsorption pump. So I guess I won't go into too much detail here, But you can see here, this is what that coating looks like. It's a very thin coating that we actually had with an ISRU company, or a company that does a lot of ISRU research, precision combustion. Um, and so we're in the process of actually testing it now. I was hoping we'd have a little bit of results by the time I came here, but it'll be soon after I come back. So the carbon formation reactor itself, so this facilitates the Boudouard reaction mostly, but there are other reactions happening at the same time. So Boudouard is CO, basically disproportionates to CO2 and carbon powder. And so we apply a catalyst to the inner walls of these reactors. And for any chemical engineers, this is basically a plug flow reactor. And once we introduce our reactants, that carbon grows off of the catalyst from the walls and slowly restricts our flow. And so it gets to a point to where our flow is restricted so much that we initiate the end of the phase where we have these attritor arms that scrape off that carbon from the walls. And then that's basically sucked out with the vacuum. And you can see some of the carbon produced here. So I'm a little low on time, so I think I'll go ahead and move on from that. So the solar thermal receiver. So once again, this is going to be designed to take in solar thermal energy from a solar concentrator and heat up our reactants up to that 475, 550 C range. So I guess really the innovation here is that we're using shape memory alloys to actually to regulate the temperatures. So we use something called a torque tube that is trained to operate at these temperatures, and it will pull a shade over if it reaches over our temperature, and it retracts when we need more solar thermal energy. So we're also integrating our two reactors. Like I said, this is actually being done at Marshall Space Flight Center in Alabama. So we're just wanting to develop our system level understanding of this chemical process to demonstrate its operation. So looking towards the future, so we're going to be continuing developing our components, developing our integration testing to actually anchor our model to have some real data there. And lastly, we're actually doing a little bit of exploratory studies on what we can actually do with this carbon. So there's been another project at NASA that's looked at 3D printing sodium-ion batteries on the Martian surface, and they need carbon as the anode material. And so we think that could be a interesting feedstock for that. So we're doing some electrochemical testing on that carbon. Also, if we activate the carbon, it could be a filter for things like VOCs. I actually am looking at absorbing CO2 as well. So perhaps it could be used in our absorption pump. Also, it could be a feedstock for different additive manufacturing processes. And so before I end the presentation, I just want to thank my awesome team here. So everyone's been doing really great work, and I look forward to another year of the project. And these are my acknowledgements. So thank you, everyone.
Thank you, Beau. It's always fascinating to see when these things can get integrated and show off full systems like this. Any questions from the audience at this point?
Yeah, about the carbon you get at the end. Do you know, like, so you get a powder at the end, basically. What do you have any information about the grain size distribution and the morphology? Because I mean, doing some additive manufacturing, we could use that. I need some information about how it is.
Yeah. So we've done a lot of testing on it actually. So I don't remember the exact particle size distribution offhand. I believe it's something like 10 to 100 micrometers. Although I can confirm that with you. The morphology, we actually have a lot of SEM, TEM, different data on that. The morphology is really interesting. It has a pretty decently high surface area. And when you look at the microscopy images of it, it has a lot of these really tiny fibers coming off of the carbon. So it's definitely really interesting. I think it could potentially work with different additive manufacturing processes. So we could, talk further to see, maybe some integration there.
Thank you.
Thank you.
Thank you. Oh, there's one more question. Go ahead. Yeah.
Hi, thanks. Carl Hibbert, APL and LSAI. Carbon thermal is being explored by multiple groups funded by STMD. One of them is Sierra Space as well, which demonstrated its reactor in the JSC chamber. Are you to what level are you integrating with Sierra Space, considering their pretty advanced technique? This looks very synergistic with what they're developing.
Certainly. Yeah. So Sierra Space, from what I've seen from their publications, they are they typically talk about methane as their carbon source. But I have heard that carbon powder could be a potential feedstock for their process. If they do decide on carbon powder as their reactant, then we would certainly be looking to integrate.
Yeah, they may have made that switch already.
Oh, okay. Then I will certainly be talking to them. Yeah, yeah. We've been talking to them quite a bit. And from what I heard, I didn't know they made that decision yet, but if they have, that'll definitely make me happy.